Hi everyone, thank you very much for tuning in. My name is Roei, and this talk is titled Hardness versus Randomness Revised, Uniform, Non-Black Box, and Instance-Wise. It's based on a joint work with Lijie Chen from MIT. And the take-home message and what we're going to see in this talk is the following. We're going to see a new version of the main paradigm in the randomization, which is hardness to randomness. We're going to connect non-black box de-randomization algorithms with new types of lower bounds for probabilistic algorithms. And we're going to introduce a new and general framework for hardness versus randomness of the non-black box type, which in particular would yield conclusions such as P equals BPP, and a free lunch de-randomization with effectively no overhead at all, and various other settings, slower de-randomization versus weaker lower bounds, average case de-randomization of limited circuits, and so on. I'm going to start by presenting the two main results in the paper, and afterwards I'll move on to describe the new general technical frameworks that gets these results and others. And let's begin by the first one, which is under the title of a non-black box approach towards BPP equals P. So just a historic recap, the main paradigm in de-randomization is hardness versus randomness, which was introduced in the 80s and crystallized into the standard textbook form that we know today throughout the 90s. And it's been extensively studied in scores of subsequent works since then. The main focus of this paradigm is an equivalence between explicit lower bounds for non-uniform circuits and explicit PRGs, pseudo-random generators for non-uniform circuits. And PRGs for non-uniform circuits can then be used for de-randomization. So, for example, the famous result of Impagliazzo and Wigderson from the late 90s is that exponential time is hard for non-uniform circuits of exponential size, if and only if there exists an efficient PRG with logarithmic seed for non-uniform circuits. And as a consequence of the existence of such a PRG, we get the conclusion that BPP equals P. And throughout this talk, whenever I say BPP equals P, I mean the promise problem version. So it's the stronger conjecture. Now, a second focus of hardness versus randomness is another equivalence between explicit lower bounds for uniform circuits and explicit PRGs for uniform probabilistic distinguishers, where such PRGs are good for average case de-randomization rather than worst case. So, for example, another result from Impagliazzo and Wigderson from the same time is that exponential time is hard for BPP. BPP is a uniform class, if and only if there exists a PRG with short seed for uniform distinguishers, which is equivalent to de-randomizing BPP on average in sub-exponential time. And for simplicity, because I just want to convey a point here, I'm ignoring some technical issues regarding infinitely often versus almost always. And let's recap just to see what I said. So I talked about two equivalences shown in classical hardness versus randomness. The first one is lower bounds for non-uniform circuits and PRGs for non-uniform circuits. And the second one is lower bounds for probabilistic uniform algorithms and PRGs for uniform probabilistic distinguishers, which give an average case de-randomization. So this is the top one, and this is the bottom one. And the really annoying thing here is that the thing that we care about the most, the conjecture that P equals BPP and de-randomization, kind of sits in the middle. It's, of course, a consequence of the existence of good PRGs. And of course, it's stronger than de-randomization on average. This is worst case de-randomization, standard textbook one. But we don't have an equivalence of this conjecture, P equals BPP, to certain types of lower bounds. And this is a classical open question that can be framed as follows. We know that PRGs yield black box de-randomization. De-randomization, which uses a pseudo-random set. The pseudo-random set is generated before seeing the algorithm and input that we want to de-randomize. And the question is whether or not this black box approach is an overkill. It's been studied for at least 20 years. We know that in some settings, for example, non-deterministic de-randomization, PRGs are indeed necessary. This is a consequence of the algorithmic method that has been pioneered by Ryan Williams in the last decade. But for the main setting of BPP equals P, we simply have no idea. The question is unanswered. And the first main result in this paper is a bidirectional connection between the statement BPP equals P and a new type of lower bounds, which aren't circuit lower bounds and aren't these classical lower bounds for probabilistic algorithms. These are new lower bounds. And of course, this connection uses non-black box de-randomization without relying on PRGs for non-uniform circuits. And let me go into a bit more detail. So I talked about a bidirectional connection. So let's start with the easier direction. It's not difficult to show that if BPP equals P, again, the promise problem version, then for every constant C, there exists a function with multiple output bits that is computable in polynomial time, deterministic polynomial time actually, and is hard for probabilistic time n to the C on almost all inputs. So to recap, for example, taking C equals 100, if BPP equals P, there's a function that is computable in deterministic polynomial time and is hard for probabilistic time n to the 100 on almost all inputs. And the statement looks deceivingly simple, but the thing is that almost all inputs is a new notion. And it is a very, very, very strong notion. It means that every machine, every probabilistic machine running in time n to the C, fails on each and every input of sufficiently large size. So notice, I'm not talking about every input length or something like that. I'm saying that each machine fails basically on all but finitely many inputs. So from a certain input length and onwards, the machine fails everywhere, no matter the input. And this looks like a crazy strong lower bound, but it's necessary for BPP equals P. This is the contents of the observation. And the main result is a partial converse. If there exists a function with multiple output bits that is hard for probabilistic time n to the 100 on almost all inputs, just like we said now, and in addition, this is the additional constraint, it is computable by circuits of medium depth. The hard function is computable by log space uniform circuits of polynomial size and depth, say n squared, then BPP equals P. Again, in the promise problem version, stronger version. So what we see here is a bidirectional connection between worst case de-randomization, such as BPP equals P, and this new type of lower bounds on almost all inputs. And we're not getting into details in this short talk, but let me just mention that this is a robust connection. You toy with one side, you still get a connection to another version on the other side. The connection is robust to playing with the hypothesis and conclusion. It is general, not only for BPP equals P, but for any type of worst case randomization. And it seems intuitively a right hypothesis for the randomization. This goes back to the 70s and a conjecture put forward by Cozen, which is very broad, that talks about simulating one type of machine by another type of machine, like BPP equals P, and lower bounds within these two types of machines. For example, like here, a deterministic machine can compute a function that's hard for probabilistic machines on almost all inputs. Let's move on to the second main result in the paper, which focuses on a conclusion stronger than just BPP equals P, that we call super fast de-randomization, or alternatively free lunch de-randomization. And this is a great recent question. The statement BPP equals P means that for every time-bound t, we can de-randomize probabilistic time t in deterministic time t to the c, where c is some constant. And the problem is that C can be huge, it can be impractical. C equals 1,000, C equals 1,000,000. It's the randomization with a huge unspecified polynomial overhead. And very recently, Doron, Moshkovitz, O, and Zuckerman raised the question of whether or not we can de-randomize quickly with a controllable C, fixed polynomial time. What is the actual cost of de-randomization? And ideally, can we get de-randomization without paying for it at all? They showed that under strong circuit lower bounds, we can get de-randomization with essentially a quadratic overhead. So the constant C is very close to 2. And in a follow-up work, Lijie and I showed that assuming one-way functions and lower bounds that are necessary for the conclusion when using PRGs, we can de-randomize time t in deterministic time n times t to the something that is very close to 1. So for a very large t, this is great, because n doesn't really matter, and this looks like de-randomization with almost no overhead. But the problem is that for a small t, this is again a noticeable overhead. For example, when t is linear, we're de-randomizing probabilistic linear time, we're again paying a quadratic overhead. And in this work, the current work, we show how to do better. We show that under appealing uniform lower bounds, randomness can be deduced to be indistinguishable from useless for decision problems and for natural search problems. Specifically for every constant epsilon, which is as small as you want, we can de-randomize probabilistic time n to the k effectively in deterministic time n to the k plus epsilon. So the de-randomization has essentially no cost, and the word effectively here means that no polynomial time observer can find a de-randomization error with non-negligible probability. So the de-randomization looks correct to any polynomial time observer, and we pay almost no overhead. And this is, of course, something that we get with non-black box de-randomization. The second part of this second result concerns explicit constructions, so search problems. So think of constructing objects that have a good property, pi, and this property is dense. The second part of this result says that if pi is recognizable in time n to the k, then we can explicitly construct objects deterministically in time n to the k plus epsilon. So essentially, constructing objects with good properties costs no more than recognizing this good property. Those were the two main results in the paper, and as I said, there's a bunch of other results, but I want to move now to speak about the new paradigm that underlies this result. So what is really going on here is that there is a new way to do hardness versus randomness that yields these results and yields the other ones too. And this is the way that has these adjectives in the paper's title: uniform, non-black box, and instance-wise. And to explain it, let's go back to the textbook's approach. So here is the setting for the randomization. We want to simulate a probabilistic machine M on a given input. And without loss of generality, by using a complete problem, the input is a description of a Boolean circuit C, and M is the machine that just draws a random R and outputs the evaluation of C at R. So basically, without loss of generality, we get as input a description of a circuit C, and we want to approximate the acceptance probability of C up to some small additive error, say 1/10. So here is a visualization. On the left, we have the input C, and on the right, we have the distinguisher, which is the same input C, which gets strings R. So we look at the input C, and what do? If you open up a textbook and look at the hardness versus randomness approach, the classical one. Well, first, we compute a truth table of function that is hard for all small circuits. This truth table is F. Then you apply a sequence of transformations to this truth table F. This is what you may recall as the Nissan-Wigderson and the relatives of Nissan-Wigderson. You apply codes, you apply designs, and basically you transform F into a pseudo-random set of strings, R1 up to R capital N. Capital N hopefully is not too large, maybe it's polynomial in the size of C. So this pseudo-random set is what we will use as a PRG for C. So let's go into more detail. Given C, we compute the truth table F that is hard for circuits, for example, under hypothesis. We transform it to a set R1 up to Rn using codes and designs, etc. And we evaluate C on this set R1 up to Rn. And then using an argument on this with the style of Nissan and Wigderson from '94, we have a reconstruction. If C is a distinguisher for R1 up to Rn, then the hard function F has a small circuit, which is a contradiction. And we conclude that this set is pseudo-random for C. Why did I go into all this detail? To highlight the main point, which is an obvious shortcoming of this entire approach. We basically made no use of the input C when generating the pseudo-random set R1 up to Rn. Basically, we computed the hard truth table F from thin air, transformed it into a pseudo-random set, and only then used the pseudo-random set. And the basic new thing, this is the fundamental thing, this is the most important thing in the new approach, is that instead of generating pseudo-randomness from thin air, we are now going to use the input C to generate a pseudo-random set that works specifically for C rather than for all circuits. So instead of just computing some F by ourselves, we're going to transform C into F of C, which depends on C, and then transform F of C into pseudo-random sets. This is the main innovation, using the input to generate pseudo-randomness for that specific input. And of course, this suffices for the randomization, because when trying to de-randomize, we have this input in front of us. And as an insightful reviewer said, it's not that this approach has not been tried before. This is obvious. This is the first thing that you'd want to do. And there is a long line of works, at least in the recent 20 years, dating back to Goldreich and Wigderson from 2002. But it wasn't known how to use the input to generate pseudo-randomness. And in terms of techniques, before getting to that, okay, so there is an abstraction here put forward by Goldreich in 2010, which is called targeted PRGs, or targeted heating set generators. These are PRGs that get as input a circuit C and efficiently produce a pseudo-random set for this C. And Goldreich showed that this is both necessary and sufficient for the randomization. And this is precisely what we do in this paper. As you have seen a couple of slides ago, we use C to generate a pseudo-random set for C. We construct a targeted heating set generator in PRG. Now, materializing this approach, making the high-level idea works, requires, of course, new technical ideas. And the main technical idea is a connection to doubly efficient proof systems. So F of C, the role of F of C here, the thing that we are going to use to generate pseudo-random sets, is prover strategies in a doubly efficient proof system that asserts the value of F of C. In more detail, we will construct a targeted heating set generator that relies on the doubly efficient proof systems of Goldwasser, Lijie, and Rothblum. And the pseudo-random strings in this targeted heating set generator will be based on the prover strategy functions when instantiating this proof system for the specific input that is given to us. And the correctness that we show is a reconstruction argument that uses specific properties of this proof system. Let's recap and do a quick digest. This is indeed a high-level and very rushed talk. I want to go over the main messages. So the key takeaways, we saw a new way to do hardness versus randomness, which is general in many settings. It's uniform and non-black box and depends on the input. We saw what may be the right hypothesis for BPP equals P, connecting worst-case randomization to lower bounds for almost all inputs. And we saw that under uniform strong high assumptions, randomness might be indistinguishable from useless for decision problems and for natural search problems. And in case you're interested in more, you can head to the paper. It's accessible. It has drawings and diagrams and explanations, and we use sticks, so it has pictures. There are 2 more elaborate slide decks available, both on Lijie's website and in my website. You'll get more details there. And we also very much like emails, so please feel comfortable dropping us a line. That's it. Thank you very much again for tuning into the talk.